Welcome to our last section on mathematical modeling. In this section, we're going to look at trigonometric models. And the key property of these is that they're going to model phenomena that are periodic. The reason we use trigonometric functions in this case is because, well, they are our go-to example of periodic functions. That is, functions whose values repeat after a certain point. So just recall that sine, cosine, secant, and cosecant are periodic with period 2 pi. So after an interval of length 2 pi, they are back to where they started. Sine of theta plus 2 pi is equal to sine of theta. And similarly for cosine, secant, and cosecant. Tangent, on the other hand, is pi periodic, as is cotangent. So what kinds of phenomena could we use trigonometric models for reasonably? Well, any sort of phenomenon that tends to repeat itself in a constant way. So these can be used as bases for problems involving anything that is repeated over a set schedule, such as temperature patterns over time. The idea here being that the temperature patterns repeat themselves year on year. It's cold in the winter, warmer in the spring, hot in the summer, colder in the fall, and then once you hit winter again, you're back to where you were 1 year ago. And you just keep repeating this process over time. This is not quite accurate, of course. There is long-term change over time. Over years, things get colder or warmer depending on the situation. But as a basic model, one could reasonably use trigonometric functions. One could also use them to model certain biological species. Now, keep in mind that we already discussed using exponential functions to model biological problems. So why would it be reasonable to use trigonometric functions as well? Well, think about the weakness of an exponential model. An exponential model says that my growth will be unbounded forever, that I'll always be growing at this sort of really fantastically rapid rate. That's not really reasonable, since population growth is, in general, constrained by the ecosystem, by the amount of resources available. So a trigonometric model solves this by saying, well, start at a certain point, grow up to a certain point, and then you reach a saturation level. And maybe you start to decline. And then you get to the bottom and you start to grow again. This might also be unreasonable, that maybe after a certain point you stop growing but you don't decline. But it is a useful technique to have in your arsenal. Many times exponential models will be combined with trigonometric models to kind of get the best of both of their respective worlds. One can also use these types of models for, say, financial markets, which perhaps also, one could say, illustrate this type of periodic nature. So what would a model for a trig function, what would a trigonometric model look like? We would look something like f of x equals a constant times sine of x, or sine of bx plus c plus d, or cosine, potentially even tangent. So what are the roles of these constants here? There's 4 of them. So A here determines the amplitude, which is the gap between the biggest value and the smallest value. So you can think of this as sort of the size of the waves of these periodic functions. If A is large, I have a big wave, big gaps between the peaks and valleys. If A is small, then I have a little wave, not much of a gap between the peaks and the valleys. B determines the frequency, or how rapid this wave is oscillating. If B is large, I have very rapid oscillations because that big B helps me reach my period of 2 pi quickly. If B is a number close to 0, like say 1/10 or 1/100th, that slows everything down. My frequency is low, so it takes me a long time to complete one full oscillation. C and D we've already seen. These determine lateral shifts, and D determines vertical shifts. It is typical to have all 4 of these constants interact for a particular model. That is, if I show you some sort of plot of a trigonometric function and ask you to write me its formula in the style of f of x equals something, all of these may have to play a role. And they'll typically also play a role for real-world problems, where I describe some sort of physical scenario and then ask you to write a mathematical model for them. So let's get some practice here. We'll start with the mathematics. I'll show you the plot of a trig function, and I'll ask you to infer from the picture what is the formula for the function. Let's get started. So here I have a sinusoidal function. Looks like maybe sine or cosine. Let's try and figure out how to represent it. So first let's look at the length of one period. I start at 0, and by 3.14 I've repeated myself. So the period here is equal to pi. That's how long it takes for me to repeat. So this means I'm certainly going to have a multiplier inside of my argument. I'll definitely have to use this constant b here. How about the maximum value? Well, that's 3. And the minimum value is -1. So this tells me that the difference between the max and min is 4. So this tells me that I'm going to have to use this constant a out front, because usually the difference between the max and the min is only 2. But here it's 4, so it's twice as big as normal. And then let's look at one other thing. Let's look at the value when x is equal to 0. I get 1. So my starting point is 1. But the basic picture looks more like sine than cosine. I start somewhere, I grow for a little bit, then I decay, and then I start to grow again. Whereas cosine starts at its maximum value and then just falls off into decaying right away. So what could this be? Let's use a sine function. I have to compensate for the fact that my period is more rapid than normal here. So I'll put a 2 pi, or rather a 2x inside. Now my amplitude is also bigger than normal. It's twice as big, so I'll put a 2 there. Now this isn't quite the complete picture though. What does this give me? This would give me approximately this picture. Like this. So I'm missing this vertical offset, but I can easily add that in. That's the plus d in our model. So I'll add in a +1, and now I hit the nail on the head. So here I had to adjust the amplitude and the frequency and this vertical offset. I didn't have to do a horizontal offset, so I only had to use 3 of my 4 model parameters. So here's another one. Now let's again examine the period, and it takes me from 0 to about 25 to do one full cycle. So this tells me that my period is something like 8 pi, which is about 25, a little bit more. So I'm going to have a frequency multiplier, but it's taking me a long time to do one cycle. So I'm going to have a number between 0 and 1 playing the role of b here. How about the maximum value? Well, the max is equal to 2, and the min is equal to 0. So the difference between max and min is 2, which is what it normally is if a was equal to 1. So I'm not going to have to multiply by a number other than 1 or -1 for a. But what kind of behavior do I have here? Well, it looks a little bit like cosine. It starts at something and then just increases without bound until I get to here, until I get to 4 pi. And then it starts to decrease. Now, cosine has the opposite behavior. It starts somewhere and decreases for half of the time and then starts to increase again. So in this case, I'll write this model as follows. At 0, I should be 0, so 1 minus cosine of x over 4. So let's check that this does the trick. So at f of 0, I have 1 minus cosine of 0 over 4. So 1 minus 1, so 0. So that point is correct. Let's try f of 4 pi. This is 1 minus cosine of pi. So 1 minus negative 1, so 2. So that point is correct. And lastly, f of 8 pi is equal to 1 minus cosine of 2 pi. So 1 minus 1, so 0. So I get that point correctly too. So for this problem, I followed the same procedure. I first computed the frequency by looking at how long it takes to complete one period. Then I got the amplitude by looking at the difference between the max and the min. And then I fit a model to it using this offset. So let's look at a real-world example now, as opposed to looking at a plot of a mathematical function and trying to compute the rule for it. So here we have a Ferris wheel with a radius of 50 feet, which rotates once per minute. At time t equals 0, a chair begins to move, starting at the lowest point on the wheel, which is 2 feet above the ground. Our goal is to write a model for the height of the chair as a function of time. So our first question is, why is this reasonable to cover in submodule 5.3? Why is it reasonable to use a trigonometric model here? Well, remember, the most salient aspect of a trigonometric model is the fact that it is periodic. So it models phenomena that repeat themselves. Does this make sense here? Well, sure. A Ferris wheel starts at the bottom, goes to the top, then goes back to the bottom, and then repeats. So it's following the circular loop, which means that the periodic function is reasonable for this. So what do I know? Well, let's say that h of t is equal to the height of the chair after t minutes. So what do I already know? Well, I know the function's value at several points. I know that h of 0 is equal to what? Well, it's going to be equal to the height at the beginning, so 2. And I also know that after 1 minute, it's completed a full rotation. So I've gotten back to where I started, so 2. Well, that's not really very helpful. All this really says is that I start somewhere, and then after a given amount of time, I get back to where I started. How do I fill in the real details of this function? How do I really kind of get the meat of this function? Well, I want to use the fact that at the top, I know how high I am, because the radius of this wheel is given. It's given as 50 feet, which means my picture is like this. I start at 2 at the bottom, and then at the top, I've added 100 feet. Because the diameter is 100, so at the top I'm at 100 plus 2, so 102. So I know that h of 0.5 is equal to 102. So with this, I can fit a model. I start at 2, halfway through a cycle I want to be at 102, and then at a full cycle I want to be back to 2. But think about it like this. The first half of my cycle I should be increasing in height. I should be going up. In the second half, I should be going down. So I want to find a trigonometric function that represents this. That is increasing for the first half and decreasing for the second half. Does sine follow this? Well, not really. Sine is increasing for the first quarter, then decreasing for the middle half, then increasing for the final quarter. How about cosine? Well, cosine is decreasing for the first half, then increasing for the second half. So this is actually pretty close to what I need. All I need is for the roles of increasing and decreasing to be switched. So I'll look at negative cosine, which is increasing for the first half and then decreasing for the second half. So this is like negative cosine of x here. So I'll use that as the basis for my model. So I'll say h of t is going to be something minus cosine of t. But what do I need to fit the parameters to? Well, at the top I need to be at 102, at the bottom I need to be at 2. So I'll put 52 here and 50 here. So let's check if this makes sense. H of 0 is 52 minus 50 times cosine of 0, which is 2, so that's correct. H of 0.5 is 52 minus 50 times cosine of 0.5. Cosine of, sorry, I need a 2 pi in there. 2 pi. Cosine of 0.5 times 2 pi is cosine of pi, which is negative 1, so 102. And then back at the start, I'm at 2 again. So our final correct model here is 52 minus 50 times cosine of 2 pi. And the 2 pi there is to represent the fact that after 1 minute, I've done a full cycle. So I want 1 minute to correspond to 2 pi radians, which is how long it takes me to do one cycle. So in this case, all we had to do was extrapolate the key information from the problem. Where do I start? Which direction do I move? Up first. Where do I end at the top? And how long to get back to the bottom? With those tools, we were able to write a trigonometric model. Keep in mind we could have used the sine function, but we would have had to translate inside the argument. So I think that this is a more efficient way to do it. If you find these types of problems difficult, I understand. Trigonometry is probably the most difficult aspect of the CLEP exam. So keep reading the lectures I've prepared for you. Keep looking at our supplemental readings and work on the exercises we prepared, and you'll be in good shape.